Hello everyone, my name is Nicholas King, and I will be presenting my project on parallelized exoplanet detection using machine learning with test data. This work covers end-to-end data processing, from pre-processing and feature extraction to a CNN classification model, plus a dashboard that visualizes predictions in real time. We'll dive deep into how I handle parallelization with Python to process large test datasets efficiently. Today we will walk through the motivation for parallel exoplanet detection, the tools and techniques used for concurrency and parallelization, the CNN design for time series analysis, and how Angular-based dashboard integrates with our Python backend. Finally, we will summarize the results and discuss for future improvements. The Transiting Exoplanet Survey Satellite TESS is a NASA mission launched in 2018, designed to survey large portions of the sky and discover exoplanets by analyzing brightness variation in stars. Unlike the Kepler mission, which focused on smaller regions of space, TESS observed a broad swath, or sectors, of the sky for about 27 days each, looking for dips in brightness that could indicate a planet crossing in front of its host star. Since TESS aims to cover nearly the entire sky, it generates massive volume of light curve data for millions of stars, far more than can be realistically inspected by any single astronomer or a small research team. Each star's light curve can obtain tens of thousands of brightness measurements, spanning weeks or months of observation. How we can identify exoplanet transit in these light curves is challenging for several reasons. One, subtle signal. The fractional dip caused by a planet is often very small, especially if the planet is only a fraction of the star's radius. Two, noise and artifacts. Instruments, errors, stellar variability, cosmic rays, and other noise sources can obscure or mimic transit signatures. Three, huge data volume. TESS observes millions of stars. Analyzing them sequentially for potential planet candidates can become extremely time consuming. Given these challenges, robust large-scale data processing is essential. Doing everything sequentially, i.e., star by star, step by step, can be infeasible, especially when each step, such as data cleaning, feature extraction, model training, involves CPU-intensive operations. This is where parallelization comes in. By splitting the data and the tasks among multiple CPU cores, or even GPUs, we can process many stars-like curves in parallel. This drastically reduces runtime. For instance, removing nans, not numbers, outliers, and flag data points from thousands of files simultaneously can be faster than purely sequential approach, depending on the hardware. Meanwhile, detecting planetary transits among noise calls for powerful classification models. Convolutional neural networks, CNNs, originally popularized in image recognition, can also handle 1D time series data extremely well, learning the characteristic shape of the transit dip as it appears in a brightness curve. They excel at distinguishing genuine transit events from noise or stellar variability, making them an ideal choice for test-based exoplanet detection. Putting it all together, Tesla's enormous data stream demands parallelized machine learning driven pipeline that can handle data cleaning, feature extraction, and classification at scale. By dividing the workload among multiple processes or threads and leveraging CNNs for accurate transit detection, we achieve a pipeline that's both fast and accurate, able to keep pace with Tesla's continuous flow of light curve data while maintaining high detection performance. TESS detects exoplanets using a method called transit photometry. Essentially, when a planet crosses in front of its host star, from our point of view, the star's brightness dips slightly. This dip can be extremely subtle, sometimes only a fraction of a percent. Yet, if it repeats periodically, that's a strong indicator that a planet may be orbiting that star. However, test data can suffer from various forms of noise, everything from inherent stellar activity, like star spots or flares, to measurements artifacts introduced by spacecraft. Additionally, like scattered light in the camera, changes in thermal conditions, or partial data gaps can produce false positives or confuse our algorithms. One of the biggest challenges in exoplanet detection with test data is the sheer volume. We have files upon files of light curve data. Each can be tens of thousands of measurements. Doing all pre-processing, feature extraction, and training in a sequential manner would be extremely time-consuming. In Python, parallelism can be achieved in multiple ways. Because of these tasks, cleaning, loading, feature extraction are CPU bound. We often rely on concurrent futures model to spawn multiple processes rather than threads, thereby circumventing the global interpreter lock (GIL) within the codebase. For example, in our datafetcher.py at line 44, the creation of a thread pool executor to submit download tasks for each file. The collection of the downloaded results using concurrent futures as completed to process the futures as complete on line 55. This code uses Python's thread pool executor to download files concurrently in an IO-bound task. Here's a step-by-step breakdown. A thread pool executor is created with a maximum of 4 worker threads. This allows up to 4 downloads to occur at the same time without blocking the main thread. For every object here called TPF in the variable search result, the expected local file path is constructed using the download directory and file name attribute of the TPF object. The code checks if the file already exists. If it does, it logs that file and skip and adds to the TPF object a collection TPF collection. If not, it schedules a download by submitting TPF download to a thread pool executor. The future return from the executor.submit is stored in a directory future2tpf with a TPF as a value. Once all tasks are submitted, the code iterates over the futures as they complete. The future.result is used to retrieve the result of each download. If a result is returned, it is appended to the collection. If an exception occurs during the download, the error is logged. Overall, this design efficiently handles file downloads in parallel while ensuring that already download files are skipped and any errors during the downloaded are appropriately logged. And in our uh, function segment light curve, it will determine the number of full segments that could be made by performing an integer division of the total number of steps by the segment length, and then it will use concurrent extraction of the segments with a helper function. Extract segment is defined to slice the flux array for the ith segment, and then a thread pool executor is then used to process these segments concurrently by mapping the extract segment function over the segment indices. This speeds up the extraction when there are many segments. And in our train.py, operations like converting labels to one-hot encoding, applying light curve augmentation, and later resizing batches are performed using ds.map with num parallel calls and equals tf.data.autotune. This instructs TensorFlow to process multiple elements correctly based on available CPU cores, improving throughput. And for our prefetching call, further overlaps data preprocessing with model execution by repairing the next batches in parallel while the current one is being processed by the model. By downloading or reading multiple files in parallel, we keep the CPU or GPU from sitting idle while waiting on disk or network operations. That said, concurrency can be tricky. We must ensure shared resources like logs or certain data structures don't lead to race conditions. Python offers locks, semaphores, and synchronized queues to help us manage concurrent access. Getting these details right makes for a pipeline that's not only faster, but also more robust under heavy workloads. Now let's dive into how our pipeline is structured. We break down the process down into a couple stages: data integration, pre-processing, our model, our front-end dashboard, and our API integration. And for our training pipeline, we can further break it down into 3 main stages: the data loading, pre-processing, building the TensorFlow data pipeline, and finally model creation and training. And we'll start with that breakdown. For data loading and preprocessing, first we use Python glob module to search through our dataset directory and find every relevant FITS file. This allows us to automate the discovery of hundreds or even thousands of light curves without having to specify each file manually. Once we locate a file, a helper file function called loadFitsData opens the FITS file, identifies the correct HDU, and extracts the time and flux columns. We prioritize PDC SAP flux because it's already undergone instrument corrections, giving us cleaner signals from the start. Next, each light curve is standardized by subtracting its mean and dividing by its standard deviation. Thanks to a function called normalized light curve, any nans or infinites are converted before moving on, which helps us avoid issues caused by invalid data points. To better capture transient patterns like exoplanet transits, we use segment light curve to break longer sequences into smaller, fixed-length segments, each containing 200 time steps. The step employs parallel processing with Redpool Executor to handle large datasets more quickly. If a segment is shorter than 200 steps, we pad it with zeros at the end. Finally, we match each FITS files to an external exoplanet catalog based on identifiers like TIC, ID, RA, and DEC. Files that correspond to a known or candidate exoplanet are labeled 1, while other non-candidates are labeled 0. This labeling is crucial so the model can learn to distinguish real transit signatures from false positives. From there, we create a Python generator that yields a segment and label pairs. This keeps our code modular and ensures each segment arrives in the right shape with the right label. We then wrap the generator in a TensorFlow dataset, specifying output signatures for both these time series data and the label. This is our entry point into TensorFlow's high-performance data pipeline features. As mentioned before, each segment goes into the model. We apply two mapping functions in parallel. The first converts the label into one hot format. The second introduces Gaussian noise to the segments. Adding noise is a form of data augmentation that helps the model generate better, especially in cases where real-world data can be noisy. The dataset is then cached so we don't keep rereading the same data from the disk. We also shuffle it with large buffer, ensuring each pass through the data each epoch is randomized, which prevents the model from overfitting to fixed order of samples. Next, we group data into mini batches according to a predefined batch size and apply any necessary padding to make sure all the segments fit in a uniform shape. This step is essential for efficient trading on modern hardware. Finally, for architectures that expect larger spatial dimensions, we resize the original 11 by 11 input to 127 by 127. This ensures our final input shape aligns perfectly with the model's requirements. In our model building and training section, we defined our CNN structure with a function called buildCNN. It receives input shapes like 200, 127, 127, and 1, reflecting time steps, the upscaled spatial dimensions, and a single channel for flux. We train the model using model.fit, leveraging all the benefits of pf.data pipeline, such as a parallel loading and augmentation in each epoch. This setup helps keep our GPU or CPU constantly fed with data, minimizing idle time. After the training completes, we finally then save our model architecture and weights to the disk. This allows us to reload it for later for validation, inference, or further fine-tuning as new data becomes available. To sum up, this entire pipeline from automated file discovery to final CNN training ensures that the raw FITS files transform seamlessly into a model that can quickly distinguish exoplanet candidates from non-transit. By using parallel techniques and TF.data's built-in optimizations, we can make the most of our hardware, whether it's a single CPU or GPU-enabled environment. We will now deep diver into our preprocess.py, which does data cleaning, normalization, the segmentation, feature extraction, and parallel execution, as all mentioned previously. The preprocess.py script is where the main data transformation happens. First, we remove invalid data points, nans or flag values that might result from tested onboard instrumentation issues or cosmic ray hits. Next, each light curve is normalized, typically by subtracting its mean and dividing its standard deviation, as mentioned previously, though our neural network doesn't struggle with vastly different scales from star to star. To accelerate this, we use a process pool executor and split the dataset into logical chunks, one chunk per process. Each process runs the cleaning, normalization, and segmentation in parallel. Segmentation means taking a long light curve and dividing it into smaller windows so that if a transit exists, we can isolate it, the relevant portion, more easily. We also compute some basic statistical features, mean, standard deviation, skewness, in parallel. This parallel approach cuts down pre-processing time drastically, especially with large test data volumes. However, it's vital to manage overhead. Spinning up many processes has a cost. We typically choose the number of workers to match the number of physical CPU cores or slightly less, striking a balance between parallel speedup and overhead. Our model uses 1D layers for time series signals, pulling dropout for dimensionality and overfitting control, batch norm for training stability, sigmoid output for binary classification, exoplanet or non-transit, parallel data loading, tf.data pipelines with prefetch concurrency. Here's the API, and at startup, the code loads our model from the specified path, and then it calls our predict from file function, which takes a fits file and it will process it, get the HDUL data out of it, prioritizes the PDCA SAP flux, time and flux, converts into NP arrays. An extra dimension is added to represent the channel, making it compatible with this CNN model. TensorFlow is used to convert the segment into a tensor. Each frame is resized to 11 by 11, or from 11 by 11 to 127 to 127. A batch dimension is added so that the input shape matches whatever the model expects. The model runs a prediction on the process segment, and the prediction is stored. Finally, the function returns both the prediction and a list of raw segment data in a list form. And this predict route will take the fits file from a post, call the helper function predict from file, and it will then return the predictions in segments. Our Angular dashboard will then take a fits file from the user, then post it to that predict route from our API. It will then take these predictions and segments and display it to the screen. We display the segments in chart.js, so it will take each of the points of the light curves and draw it out to the screen. And we will also give the user a preview in our Aladdin Light preview of the fits file. It will also display a table of the segments, each marked as exoplanet detected or non-transit, based on the probability of what our model predicts what class it would be in. This real-time feedback is crucial for quick follow-up analysis. So putting it all together, we can choose our fits file. We will see a preview of our fits file. And our code will then, once we upload, take segments of the light curves from this fits file, apply it to our model. Our model will then predict each segment to see if it's non-transit or an exoplanet detected, and it will show us each of those segments. So based off our model, no exoplanet was detected, and there was all non-transit class, and here are the light curves for each segment. And this is from the HLSP. If we go and find one of our files from tests, we can take a test file from 2019, reload, take that test file from 2019, upload and predict. We can see that no exoplanet was detected in 91 segments. And here are all the light curves of the segments. As we can see, it's very noisy. There's no arc of a noise, all noise. There's no light bend from a planet passing over its host star. And so we could go over this and find one that actually does have an exoplanet. Um, right now, the model is only trained off of 5,000 directly from HLSP and tests. The upcoming model will be based off of a larger production data set, and it should be more accurate based off of that data. And we'll get better percentages than just is or is not. The real takeaway from this slide and our results is that we were able to increase the speed by pre-processing, using parallelization, using our concurrent features from 14 hours to 7 hours. And I will provide those times later. But and I will also describe the issues as we ran into. We used um, a first iteration of this exoplanet dashboard detection, and the second iteration is our 7 hours, and we use the first one with sequential. One of the main challenges that I faced while doing this project was overfitting data. So the data was very similar, as you saw on the validation from the preview, that all of the data that was used was very similar. So the model could cheat and learn and remember instead of actually doing the proper learning as the model. So getting a production data set, which is in work right now, is one way that I'm getting around that. The data acquisition, there is petabytes of data that is provided from tests in the MIT and NASA database. So I can't just, download that to my machine because I don't have enough storage for that. Another challenge was the first iteration of this exoplanet dashboard actually streamed the data from an AWS S3 bucket, and streaming data had too many network issues. So streaming it was a lot slower and couldn't rely on the hardware that was on my machine to handle the brute force of processing the data. And another challenge was early on, there was a TensorFlow dependency conflict with the rest of my project, and trying to run it in TensorFlow in a virtual environment, aside from where all the other dependencies were, was a huge headache, but eventually I got that resolved. And that is the conclusion. Um, I will add a follow-up portion to this video, or a separate video of the working with the validation data set of I think 20,000 plus files compared to the 5,700 files that this model was trained on, and it will be evenly balanced between HLSP dataset and the test dataset, which will provide more accurate feedback. And I will also provide the times on the training of that, because it was also slower than 7 hours because I added more of the concurrent features during the pre-processing, as I showed previously in the video that is currently training on. So thank you everyone for their time. This project was super fun and I learned a lot, and hopefully this demonstrates my ability in parallelized processing. Thank you.